Alright, welcome back to mathematics. In this video I will briefly go over the exponential functions and logarithms script. So we started the topic with the movie from the 70s of Powers of 10, where they zoom out from a man's hand into the macrocosmos, to the edge of the universe, or at least was then known as the edge of the universe, and then zoom into the hand, into the microcosmos. And we said, or we saw that because, well, it's powers of 10, right? They go from 0 meters from the hand to 10 meters to 100 or 10 squared to 1000 or 10 to the power of 3 and so forth. And this grows so quickly that if you want to plot the ST diagram, and say here on the y-axis you have the distance from the hand, on the x-axis you have t, of course, then you run into problems, because it grows so quickly that no matter what you put as a unit distance here, even if you put 1000 kilometers as a unit distance, the graph then just escapes into nowhere, and you can't adequately sketch it unless, and we saw that, you put not the actual meters, but only the powers of 10 to the whatever exponent you have at the moment on the y-axis. And that we did, and said, okay, I have 1, 2, 3, and I believe it went all the way up until 24, and then we zoomed in here, -1, -2, and so forth. And note that here, of course, even though the x-axis or the t-axis here usually marks a distance of 0 relative to the y-axis, here actually the distance would be 10 to the power of 0 or 1 meter away from the hand. But that's, I put that wrong here, sorry. We start with 1 meter away from the hand. And that, of course, represents the situation adequately. And then if you move into the negative here, even notice that 10 to the power of -3, remember from rational exponents, that's just 1 over 10 to the power of 3 or 1 over 1000. That's not something actually negative in terms of distance. It's just really, really close in the sense of 1 over 1000 meter. So it really gives us a framework where we can sketch the graph adequately. And what we saw is that then, I won't be super detailed here, you zoom out to the edge of the universe, you take a little pause here, and then you zoom in again even faster, and then you're 1 meter away from the hand again, and then it slows down a little bit and zooms in as far as possible. And now you have or we had adequately sketched this in a coordinate system, with the payoff that we didn't here, distance from hand is not in meters, but in let's say 10 to the y meters, where y is then 1, 2, 3, or -1, -2, and so on. And we said that, yeah, this was the problem of labeling the axis, in the sense of that we had to not linearly as usually just pick a unit distance, and then the distance from here to 1 is the same as the distance from 1 to 2. Here, distance from here to 1 is from 1 meter to 10 meters, so it's 9 meters, whereas the distance from 1 to 2 is from 10 to the 1 to 10 to the 2, so 10 to 100, so 90 meters, and so forth. So the distance varies, but it allows us to sketch the whole journey adequately. And what we did basically is we ignored, we said, okay, on the one hand, we have here 10 to the, let's say 0, 10 to the 1, 10 to the 2, and so forth. In general, 10 to the n meters. And what we isolated here is just then 0, 1, 2, and so forth, and then n. And this translation from here to here, or from here to here, is what actually sort of motivated the whole topic. In one direction, from right to left, it's sort of easy to see. If, let's say, this here is x, then this here is just 10 to the x. So here for the right to left, I just do 10 to the x. What we're concerned with is how do we get from left to right. And that's where the concept of the logarithm kicks in. We then moved towards the definition of the logarithm via exponentiation. So we said some equations like 2 to the x is equal to 32, easily solvable because you know that 2 to the 5 is 32. So then, because the bases are the same, the exponents have to be the same as well, lands you at x equals 5. What about 2x equal to 3? That is a little bit more problematic because 3 is not a power of 2. So here we can't use this trick. And that led us to the definition of the logarithm, where we said we define the logarithm via exponentiation. So a to the x is b if and only if, and by this double arrow I mean we can translate the left hand side to the right or the right hand side to the left, so they are logically equivalent and imply each other. If and only if log a of b is equal to x. And this is the base to the whole topic, or the core of the whole topic. And basically you can solve all the exercises with this double implication or with this equivalency, because you can always translate something exponential into something logarithmic or vice versa. Note that here you have to be careful that you don't mix up the two bases and the exponent. So be sure that you really know how to translate left hand side, often called the exponential form, into the right hand side, often called the logarithmic form. One sort of maybe a way to think about it is that you always go in circles, in the sense of here I would do a to the x is equal to b, so counterclockwise in a circle, or log of base a of b is equal to x. That's one way where you can sort of learn it by heart a little bit, but just practice enough and then it will be internalized. So as an application, before we had 2 to the x is equal to 3, and that is now if and only if log 2 of 3 is equal to x. And it depends on the calculator a little bit. In some calculators you can directly plug in log 2 of 3. In some calculators you have only fixed logarithms, usually the logarithm to the base 10 and to the base e. But if you can plug in the log 2 of 3 directly, you'll see that it's around about 1.58. And then you've calculated x. So here for the exercises, make sure that you're really competent in translating exponential to logarithm form. And then you can also solve equations with logarithms and exponentials now. Here notice the old trick with e to the power of 2x and e to the power of x. E to the power of 2x, you can rewrite that as e to the power of x squared, and then the whole thing becomes a quadratic equation with substitution, and then you can resubstitute and use logarithms. We looked at the special case of the number e, which is called the Euler number or Euler number, and here we don't really use log e of x. It's not wrong, it's just that mathematicians have sort of adopted another notation called ln, standing for Logarithmus naturalis, and that is the logarithm to the base e. We discover how far the base e is special, or the number e is special, in the secunda when we look at calculus. Then for the logarithm laws, we looked at first if we have a to dx is equal to b, if and only if log a of b is equal to x. Here, for instance, you can plug in for b this a to the x, and then you immediately get log a of a to the x is equal to x. Or you can also plug in maybe I do it a little bit differently, this whole thing here, because it's equal to x, for x here on the other side, which then gives you that a to the log a of b is equal to b. And those things already hint at something that's very much sort of the core of the subject as well, that logarithm and exponentiation to the same base, they work inverse to each other, in the sense of if you first do a to the x and then you apply the logarithm to the base a to that, then just x comes out, so the initial number what you started with. Or if you start with a number b, you apply the logarithm to the base a and then you put that into the exponent to the base a, then you land at b again sort of reconfirming that those two things are inverse to each other. And then based on that you can prove different logarithm laws. We put up 3 of them, depending on the literature or the book you look in. You also have others. Those are just helpful things to rephrase logarithm expressions, and they also show you that the logarithm translates what is a multiplication into an addition if you take it apart, and vice versa, or sort of as a logical counterpart, it translates division into subtraction, of course. Note that here y shouldn't be 0, but we excluded that anyway. Here at the beginning, the definition of the logarithm. If you look here, the number in the brackets for a logarithm has to be strictly larger than 0, so that's not even a problem here. Then the third law is that if you have log a of, for instance, x to the c, then this is c times log a of x. So here it also reconfirms that the logarithm is useful to pull down stuff from the exponent, where we previously didn't really have access to, even with roots and stuff, there was no way to pull down an expression from the exponent, and now with the logarithm we can do that. And we said that, okay, logarithms by the logarithms law translate multiplication into addition, and conversely from the exponentiation you'd expect that to do the other thing, and that is true. You know from already maybe the 8th grade, that a to the x plus y is a to the x times a to the y. And here you see that addition is translated into multiplication after you take the things apart. So it really it does the opposite of what the logarithm does in terms of translation of multiplication into addition or vice versa. Then you can use that to simplify and summarize different logarithmic expression, and then maybe a little bit more as an application that then also proves useful later on, solving exponential equations. Here, always as a hint, first isolate the exponential expression. So here first go for e to the power of 3x minus 5 is equal to 7 by 2. And now, only now, translate that into the logarithmic expression, namely here would be ln of 7 by 2 is equal to 3x minus 5, and then you can solve for x. So it's worthwhile to, if possible, isolate the exponential or the logarithmic expression and then use the equivalency from the beginning. There are other ways, of course. You could also just apply a logarithm to this whole equation and then use the logarithm laws. Works as well. It's just a few more steps that you have to do. So summarizing and putting exponential or logarithmic expressions alone on one side often makes things a little bit easier. Then we looked at an application in growth and decay with a COVID example. So if we say, okay, we start this certain day 0 with a patient 0, and this patient or this person infects 2 other people, and it takes 5 days for that to happen. Then here, after another 5 days, those 2 people will have infected 2 more people, and so forth. And then you can say, okay, on day 20, you have always times 2 here. You start with 1 person and you do times 2, and then you do times 2 here. So you have 1 person times 2 to the power of, here we have 5 days. So on day 20 we will have completed that 4 times. So 1 times 2 to the power of 4. And then we saw that for totally infected people, you just have to sum up everything. So you just sum up the 1 here from the first one, plus the 2 from the next one, plus the 2 to the power of 2 from the third one here. And then if you continue, I won't sketch it all the way down, but you'd be on that level here. So you'd have plus 2 to the power of 3 plus 2 to the power of 4, and then you can calculate that. Here that would be 16 plus 8 is 24, plus 4 is 28. So in total you'd have 31 people in total infected. And then the problem is, if we go for day 31, we jump in time steps of 5 days, because they infect another 2 people only every 5 days. And 31 not divisible by 5 makes this a little bit difficult. And here we set up the function n of t is equal to n0, that's the initial amount, times q, that's the growth factor, to the power of t is time divided by r, the growth rate. So here, as an example, that would look like we start with 1 person times the growth factor. We always do times 2 to the power of t divided by the growth rate. So we only do times 2 every 5 days. So that would be our n of t. and then of course you just plug in n of 31 is equal to 1 times 2 to the power of 31 by 5. So that's the general equation or growth and decay equation here. Useful things are q is equal to 1/2 for half-life questions, and you can always sort of adjust the r if you don't multiply by the growth factor every time interval. So if you measure your time in days, but you only do times 2 every 5 days, you can put a 5 here to adjust that. I'll give you here a few examples. Maybe here for exercise 2, you start with 1,000 Swiss francs, and it takes 10 years for your money to double. So there are different ways of now solving that. You can directly say, okay, n of t is 1,000 times 2 to the power of t by 10, because we do times 2 only every 10 years. And then the question is, how long will it take for your money to triple? So here you can then say, okay, n of t, then the final amount should be 3,000. And then that gives you the equation 2 to the t by 10 is equal to 3,000 by 1,000 is 3, and then you can solve for t. Another way you could solve that is also that you say, okay, it takes 10 years for your money to double. So I start with, again, 1,000 times. And now I say, okay, I don't directly go for the 2 and the doubling here per our formula. You could also say, okay, I go just times q to the power of t is equal to 2,000. And here I know that my t, if I double, is 10. And then you can solve for the q. So here q to the 10 would be equal to 2. Or if you then take the 10th root, your q would be the 10th root of 2. And notice by rational exponents, that's 2 to the power of 1 by 10. So you land at the same sort of idea, but it's just a different way of thinking about it, or a little bit of a different approach. Some people like the general formula more and just set it up that way. Some people like the more maybe intuitive approach like that, to go for the q first and then say, okay, this is my q, and I just take the 10th root of 2 as q more. So yeah, pick whatever way makes more sense to you. Then here note that also for percentages, if you only have 76% of whatever carbon-14 the initial amount left over, then this implies a very specific growth factor of 0.76. So here you'd only have 0.76 of whatever initial amount you have available. So here if you start with n0 times sorry, I said growth factor. It's not the growth factor, of course, it's our final amount times 1/2, because we deal with half-life, to the t by 5668 is then 0.76 times n0. Okay, then we looked at exponential and logarithmic functions, and here we saw that as rough sketch, an exponential function always looks like this here. More or less, if you have a base like 2, so that would be the graph of n of t, and here you really see that this thing grows really, really fast, in the sense of the further you go over to the right, the faster it grows. And that's also the core problem of something like COVID, for example, where we really had the problem that the growth is so extreme that it can only with difficulty be contained. So the growth here is not linear, but it's always times the same thing, and that's what we call exponential growth. We then saw that 2 to the x maybe looks like this, a bit more precisely like this here, whereas 1/2 to the x looks like this here, and minus 2 to the x is then a reflection at the x-axis like this here. So you can play around with the exponential functions and you get different graphs. Roughly the takeaway here is 1/2 to the x can be rephrased again with rational exponents. That's 2 to the negative 1 to the x, and that's 2 to the negative x. So essentially from blue to red we replace x with negative x. If you do that, it's a reflection at the y-axis, and if you just put a negative sign in front, it's a reflection at the x-axis. Then for logarithmic functions, we saw that again 2 to the x still looks like before, looks like this here. And then the logarithm to the base 2 of x looks like this here. Both cross as 1 on the y and x axis respectively. And what we saw is that they are basically a mirror image of each other along the axis y equals x. And that's the first time you already saw that functions that behave inversely to each other complement each other in a graphical fashion, in that they are mirror images along the axis y equals x. And that's something we then later on also investigate a little bit more in the script on functions. Alright, that's about it. So as always, be sure to practice enough, because often the devil is in the detail, in the sense of you have to practice that with all the algebraic tricks and so forth that I now skipped.